Hi there, my name's Dr. Hamza Mahmood, and I'm the founder of Masteria Education. Today, I'm going to be breaking down the topic of benzenes, which is found in the A-level chemistry course. To really understand benzene, we first of all have to look at what carbon is. Carbon is a group 4 element. What that essentially means is it has the ability to form 4 different bonds. So typically speaking, when we have alkanes or when we have alkenes, carbon is bonded like this, or like this, where it has those 4 bonds there. Benzene operates slightly differently. What happens in benzene is we have a carbon which has only 3 bonds. So 1 bond there, 1 bond there, and another bond here for a hydrogen. The other electron, however, becomes delocalized, which essentially means it doesn't belong to the carbon. It belongs to the collective, essentially. So what I end up having is, I end up having 6 carbons, all of which donate 1 electron into the central ring. And this is a pi electron. So it's a pi electron from the p orbital. What happens in this case, therefore, is we form a delocalized ring. And that's why benzene has this kind of structure. So each carbon is actually only bonded to 3 other things, and the other electron is delocalized into the central ring, essentially. So this is what benzene looks like. Now, when benzene was first created, or when it was first discovered, there were different theories about what it would exactly look like. So this model here that I've just shown us, this is called the delocalized model for benzene. However, there exists another model as well, which we need to know about, and that's called the Kekulé model. So what happens in the Kekulé model is it's slightly different in that it still has the same formula. So this benzene here has 6 carbons and 6 hydrogens. This model here also has 6 carbons and 6 hydrogens because of the double bonds. However, this model is clearly different in that instead of it being a delocalized ring, you've got several double bonds seen here, alternate double bonds essentially. And this is called the Kekulé model. Now, there are several reasons why the Kekulé model isn't preferred to the delocalized model. There's actually 3 reasons that we need to know about. Reason number 1 is to do with its reactivity. So in the Kekulé model, it has alkenes in the sense of it has the functional group of an alkene. This means the Kekulé model should react how an alkene should react. Now, we know from earlier in the course that alkenes can react very easily with bromine in order to form a molecule like this in an addition reaction. However, what we actually find is when we have benzene, it doesn't react with bromine. So that means this model is much less likely. So one reason is because it doesn't react with bromine. And that's reason number 1. Reason number 2 is to do with the bond lengths. So in chemistry, bonds have different lengths depending on the strength of those bonds. So single bonds versus double bonds have different lengths. When we have this model, the Kekulé model, we would expect that all the bonds would be different lengths. So you'd have single bonds and you'd have double bonds with differing lengths. However, what we find is all the bonds are actually of equal length. And this weighs a lot more into this delocalized model where all the bonds are actually the same, rather than the Kekulé where you've got some singles and some doubles. So that's the second reason. So first was reactivity, second was bond lengths. The third one is to do with the enthalpy of something called the hydrogenation. This is basically the energy required to add hydrogens to something. So when I have my C double bond, if I add hydrogens to it, we would form a molecule like this. Now, the enthalpy of hydrogenation for an alkene, like ethene, for example, is about minus 120 kilojoules per mole. The exact number isn't super important, but you just need to know that it's exothermic. What we'd expect for Kekulé's model, therefore, is it would be 3 times that, because there are 3 double bonds here. Each double bond is minus 120, so we'd expect it to be about minus 360 kilojoules per mole. What we actually find, though, is that benzene's enthalpy of hydrogenation is less exothermic than that. It's around the 250s. Again, like I said, the exact number is not too important. But essentially what we find is it's less exothermic than expected. And it's quite important to use that wording of less exothermic, because it's not right to say it's less than expected, because minus 250 is actually greater than minus 360. So we can't say in an exam question it's less, we have to say it's less exothermic, okay? So overall, the delocalized model is preferred over Kekulé for these 3 reasons: its reactivity, its bond lengths, and its enthalpy of hydrogenation. The next thing you need to be aware of with benzene is benzene's reactions. Now, all of benzene's reactions happen the exact same way, which makes it a bit easier. To show you the reactions, I'm going to show you one which is universal across examples, and that's basically going from our benzene into nitrobenzene, which is here. Okay, so this will be the first reaction I show you, and this is universal across examples. There are a couple others which are more unique to specific examples, which I'll also show as well, but this one's universal. So with all these reactions for benzenes, I want you to remember 3 steps what you have to do. The first thing you have to do is the initial reaction. This is basically taking a catalyst, combining it with another molecule to form our electrophile. Now, as a side note, we need to actually know what an electrophile is. And an electrophile is basically defined as a lone pair acceptor. So it's a molecule that accepts a lone pair of electrons. So the first step is to do with generating our electrophile. Now, in the case of making nitrobenzene, the way we generate our electrophile is we use H2SO4 and react it with HNO3. These are both concentrated, which is an important part to remember. When these react, this will form HSO4 minus H2O, but importantly, it will form NO2 plus. And this NO2 plus is essentially our electrophile, because it's positive, it can really accept that lone pair, or that a better word of actually saying rather than lone pair is actually the electron pair acceptor, because it can be a lone pair or it can be more generally an electron pair. So the first step is generating the electrophile. The second step is the actual mechanism itself. So for the mechanism itself, we have benzene, which is here. We have our NO2, which is positive, and what happens is we have this. Now, in mechanisms, this arrow essentially shows electron movement. So what we're showing is the ring is donating an electron pair to my NO2. When this happens, this therefore allows my NO2 to be bonded onto the benzene. Now, nothing's been removed so far, so this carbon is still bonded to a hydrogen. As we said, it's C6H6. But importantly, because we've now lost some electrons from the ring, my ring is now broken, so it looks like this. So what happens is, in order to become more stable, my hydrogen needs to leave. And you see exactly where I'm drawing the arrows, which is quite important. From here, we're drawing it exactly on the ring, and here, we're drawing it from the middle of the bond into the positive center. This will then allow us to form my NO2 and my H+. The final step for all these mechanisms is reforming the catalyst. Reforming the catalyst. Now, the way this happens is, and this will always be the same across the board, we look at this molecule here, the HSO4 minus. We look at this molecule here, the H+, and all we do is we combine them. And then we reform that molecule that was the catalyst at the start which was our H2SO4. So essentially what we've got now, my H2SO4 has been reformed. And that is actually what the definition of a catalyst is. It's something which reacts, which speeds up the rate of reaction, but it itself isn't used up in the reaction. So this here is the first reaction of forming nitrobenzene. Now, as an aside, before we go on to the other reactions, it's quite important to know the name of this mechanism. So there are three types of reactions you can have in organic chemistry. You can have an addition reaction, an elimination reaction, or a substitution reaction. Addition basically means taking two things and putting them together. Elimination means when you remove something. Substitution means when you swap something. So this is clearly substitution, because we're taking my NO2 and we're swapping it with that hydrogen. So the way we name this is, we name it electrophilic substitution. Now, benzene and alkenes are different in this sense. So benzene will always undergo electrophilic substitution. Whereas alkenes, if you remember from that topic, always undergoes electrophilic addition. And the reason being is because of the electron density here. The density of electrons here is much higher, which means it's easier to react. So it can react with things like Br. Whereas here, because the electron density is a lot weaker, it has to react with things that are positively charged, essentially. Things like the NO2+. So that's the reason why these prefer electrophilic substitution. The other reason is, in order for the stability of my benzene ring to form back, we have to break this bond. So we can't have two things, essentially. So that was our first reaction. It was H2SO4 plus HNO3. Now, all these other reactions are exactly the same thing, just slightly different. So the next one, which is also universal across exam boards, is a type of Friedel-Crafts reaction. Specifically, it will be Friedel-Crafts acylation. And I'm teaching this one first because it's more universal across the exam boards. We can go into the specific ones for other examples in just a second. So to first understand this, we have to understand what is an acyl group. An acyl group is essentially a molecule like this. So this is an acyl chloride. It's very similar to a carboxylic acid, but this OH and this Cl have been substituted. So this is what we call a carboxylic acid derivative, meaning it's similar, but it's not the same thing as a carboxylic acid. And this is quite key for our reaction. Essentially, what we're going to do in our reaction is we're going to go from our benzene into a molecule like this. This is a kind of phenyl ketone. So our ketone is right here. Our phenyl is this. Why do we call it phenyl? Well, benzene can either be named benzene or it can be named as phenyl, depending on its priority. So the naming of benzene, it's a bit difficult in that it's quite seemingly random, but typically speaking, when it's the main part of the group, you use benzene. When it's not the main part, you use phenyl. So how do we make this? Again, the steps are exactly the same. Step one was generating our electrophile. So let's use ethanol chloride as our example. So that is going to be CH3COCl. What we do is we react it with a molecule known as a halogen carrier, and that will be AlCl3. So this molecule here is known as a halogen carrier. Essentially what it does is it removes the halogen from here. The way it does that is by becoming AlCl4 minus, because this will give it a negative charge, and then CH3CO plus. The plus, quite importantly, is located on that carbon. So you could draw it like that. Now, what then happens is, same as before, it's the actual mechanism. So we take our benzene, we take our C plus OCl, And then the exact type of same mechanism happens. That's the first step. Once again, that bond breaks. Once again, we have this, and we have that hydrogen. Then once again, that bond breaks. And we're left with the exact same thing, COCH3 plus our H plus. And the last step, generating the catalyst. We take that H plus, we react it with, this time, the AlCl4 minus, and we reform our catalyst and generate HCl as a result. This mechanism, as you can see, is the exact same as the previous one, and it's called electrophilic substitution, same as the other one. Before I then go on, just to keep things relevant to all the specifications, I'd like to quickly go back over nitrobenzene, and one thing about nitrobenzene, a mechanism that it also does. So nitrobenzene has another reaction that we need to be aware of. So what happens to nitrobenzene is it can actually convert into this molecule here. Okay, this is called nitrobenzene. This molecule here is called phenylamine. So the difference in the naming might seem a bit random, but essentially these are the names that you have to remember: nitrobenzene, phenylamine. So how do we go from nitrobenzene into phenylamine? It's a reduction. So we need to use a reducing agent. In this case, it's going to be tin and HCl. So these are essentially the conditions that we need. The way we do the equation, which is a common question they might ask you, is we show it like this. This H represents a reducing agent, which basically means an agent that allows something else to reduce. So in this case, it allows my nitrobenzene to reduce. And I'll explain why there's 6 in just a second. This then goes into our phenylamine plus 2H2O. Now, the way I remember where the 6 comes from is because there's 2 there and 4 there, so you must have had 6 hydrogens. The real reason, though, is because the oxidation state actually changes of this nitrogen. So this is the other mechanism that you need to be aware of. It's not a mechanism in the sense that you have to know the curly arrows, but you do need to be aware of the conditions. And it's a common question that can come up, and people often forget it. So the next little bits will be focusing on areas that are in certain specifications, but not all of them. So the next part that we're going to talk about is the addition of bromine. So if you remember with alkenes, they react with bromine very easily. These molecules, though, are slightly different. Again, we need a halogen carrier. So if we remember our step 1, it was generating our electrophile. So we take our halogen carrier. In this case, we can use AlBr3. We react with Br2, and this will form Br plus AlBr4 minus. Our second step, exact same as before. We have our Br plus, the curly arrow forms. This will then cause to break. We have the H there, Br there. Again, this occurs. This then causes our Br to be attached and to have the H plus. And the final step was reforming that catalyst. We take the H plus, the AlBr4 minus. This goes into AlBr3 plus HBr. And again, this is called electrophilic substitution. So the difference between the reactivities of alkenes and benzene, therefore, which is something we can prove, is that alkenes can react with bromine spontaneously. They don't require this halogen carrier, whereas benzene actually requires the addition of a halogen carrier. So a test would be the decolorizing of bromine water from the alkene, because it would go from Br2, which is orange, into, let's say, CH2Br, which is colorless, whereas a benzene wouldn't do that unless there's a halogen carrier. So the final mechanism, which can sometimes come up in certain examples, is Friedel-Crafts alkylation. Now, thing with Friedel-Crafts reactions is, and the reason why they're quite useful is because they actually lengthen the carbon chain. Friedel-Crafts acylation, the one we looked at before, was adding an acyl group. We're now going to look at adding an alkyl group. Alkyl just means straight, so like straight chains, basically. What we're going to do, therefore, is we're going to add a straight chain molecule, let's say this, for example, and we're going to add it to our benzene. What we'll end up with, just so we see the big picture, is we'll go from benzene into a molecule like this. So carbon, carbon, carbon. So again, you're lengthening the carbon chain, but it's slightly different in that you're adding an alkyl group rather than an acyl group. So the way this reaction happens, we take our halogen. This halogen has that Cl, a halogen alkane, sorry, which has that Cl. We add it to a halogen carrier, so AlCl3, which is the same as the one before. If you notice, the Cl and the Cls have to match. So before when we had bromine, we used AlBr3. Now we have chlorine, we're using AlCl3. What happens is, exact same thing as always, we're going to generate our electrophile. So CH3, CH2, CH2 plus AlCl4 minus. Again, exact same concept next. We're going to have our mechanism where we have our CH2, which was plus, CH3, CH3, and we show it like this. Our next step would be, apologies, it would be like this with a positive. We'd have my CH2, CH2, CH3, apologies, that should be a CH2, and then a hydrogen. Then again, that will break, and then last but not least, we form exactly what we did all the other times, which is this, with the addition of the H+. And again, in terms of step 3, it's going to be the H+, reforming the catalyst, which is here, in order to form AlCl3 plus HCl. And this is the molecule we end up with. So I hope that initial bit of benzene made sense. Essentially what we looked at what actually was benzene. So we explained exactly what benzene is. We explained the difference between the delocalized model and the Kekulé model. We looked at the 4 main reactions, which are all electrophilic substitution reactions, which all have the exact same structure. We looked at an additional rule, which was the reduction of nitrobenzene. And we looked through acylation, through bromination, and for alkylation. In terms of the additional things for different specifications, there is some specifications that make a focus on phenol. Now, phenol is essentially this. It's a benzene with an OH on there. However, it doesn't react as an OH in the sense of it doesn't react as an alcohol. It actually reacts like a very weak acid. What I mean by this is that instead of reacting how an alcohol does, it will react with certain types of bases. However, because it's a very weak acid, it only reacts with certain bases. It will only react with very strong bases. What makes a strong base? Well, NaOH is a strong base because it's a hydroxide. Whereas Na2CO3, it's a carbonate. This is a much weaker base. This is quite strong, this is quite weak. My phenol will react with this, but it won't react with this. So a good test for phenols, and this is quite a common exam question, will be how to test phenols versus carboxylic acids. A carboxylic acid will react with a carbonate. And if acids react with carbonates, they make CO2. However, phenol won't. And that's a way of testing them. The other thing with phenol, and again, this is only for certain specifications, is that it's something called an activating group. So what an activating group basically is we have our oxygen, which has a lone pair. This lone pair gets partially delocalized into the ring. Because it's partially delocalized into the ring, this makes the ring more active, easier to react essentially. By contrast, we also have things called deactivating groups. Now, these deactivating groups make the ring less able to react. So, phenol is an activating group. Essentially, what I want you to remember is whenever you have an activating group, they are 2, 4, 6 directing. Whereas whenever you have a deactivating group, these are 3, 5 directing. What I mean by 2, 4, 6 and 3, 5, because it sounds a bit confusing, is this. So imagine we have phenol like this. This is carbon 1. When I react it with bromine, what actually happens is we have a type of a substitution reaction, but it's a lot quicker, and it forms this instead. So let's talk through what's happened. 3 bromines have substituted here, here, and here. This is carbon 2, carbon 4, and carbon 6. Because 3 bromines have substituted off, that means 3 hydrogens have been swapped, which is why we get the 3HBr. And this is a reaction that some examples like OCR and Edexcel need to know about, whereas others like AQA don't. So that's essentially a rundown into organic chemistry with a specific focus on benzene. I hope it's made sense. This has been quite general across different exam boards. However, what we'll do in our tutorials is we'll be a lot clearer about what exactly is in what exam board, because the last thing you want to do in organic chemistry, when there's already so much to remember, is having to learn more. So, as a quick summary, learning about benzene, learning about kekule, this is across all exam boards, the delocalized versus kekule model. This mechanism is also across all exam boards, as is this one as well. Once we get to here, this is more targeted to OCR and Edexcel. Again, so is alkylation. It's more targeted to OCR and Edexcel, and as is this topic on phenol, more targeted to those topics. And same with here. Essentially though, what I hope we've managed to do in this brief half hour is show that benzene isn't actually this frightful topic that people think it is. It's actually very systematic, and as long as you remember the 3 core principles of generating the electrophile, doing the mechanism, reforming the catalyst, it's actually not too bad. So this was just a sample video for Masteria Education. What we're planning on doing is we're planning on running large group tutorials essentially across the weekend, where we go through the whole of chemistry, the whole of biology, the whole of mathematics for A-level and for GCSEs in this same way. It'll be affordable because compared to our competitors, they charge about £300 for just one day. What we're offering here at Masteria Education is a weekend-long revision course for just £60. That's almost 18 hours of content for just £60. That works out to be about £3.75 an hour. And in this new age where there's a lot of people going through private tutoring, which is very expensive and very unaffordable, this is an excellent alternative. Our tutors are experts, doctors, medical students who have all been through this process before, who know exactly what exam boards want and have been tutoring for many years. So don't miss out. Join the Mastery Education course. Thank you so much.